may start. I would like to introduce you a PhD student from Canada, David Elin. He's from Quebec University, and today University Laval, and today he will be talking about ultra-short pulses.
Yeah.
So,
I think I recognize most of you were at my talk last week. All right. So I've already introduced myself at the other talk. So today I'm gonna show you my research, my PhD research project, what we've accomplished so far, and like future what I plan to do also in the future. So we'll start off by just like explaining to you like the specific context of my research project, on which I'm working on a laser welding procedure for optical materials, mostly based glass materials. So in doing so, I will introduce you to typical laser welding methods, and to be followed by relatively new research on femtosecond laser welding. Afterwards, I will go on to my research project with all the results, future work, and to conclude. So, I forgot to mention that I'm doing my PhD diploma in collaboration with the company Doric Lenses right here, and the context of laser processing is interesting for them because they are looking to try to make assemblies without using epoxy glue or any other adhesive, because when you use these types of glue, it has several disadvantages. Like it's limited, you can only use assemblies in a limited environment, and also the glue has a precocious aging and slow degassing. So there are several solutions to this problem. So we can use other bonding techniques which don't require the use of glue. Today I'm going to talk to you mostly about a welding technique related to fusion welding, but using femtosecond pulses. It's not really fusion welding, you will understand later on. And I also will introduce you to the direct bonding technique. So when we use like continuous or short pulsed laser beams, there are typically three materials configurations that where welding is possible. Like in the first case here, when we have two opaque materials to the wavelength of the laser beam, the energy will be absorbed at the surface here of the incident material, and through thermal diffusion it will melt a layer at a time until it reaches the interface between the two materials. In the second case, we may join a transparent and opaque material, and we will use the transparency of the opaque material to bring the laser energy to the interface between the two materials, where will be absorbed by the opaque material and diffused thermally to the transparent material. It's hoping to diffuse enough for it to melt it. And in the third case, where we may want to join two transparent materials, we must introduce an absorbing media at the wavelength of the laser, and we typically do this by depositing a thin film coating on one of the substrates, and it will act as an opaque material to melt the transparent materials. So these are quite interesting techniques, but they do have like several limitations. Like the admissible materials are limited because we're using linear laser energy absorption. So in every case, we must have an absorbent material at the wavelength of the laser. And the fact that we are also relying on thermal phenomena, it will create a lot of residual constraints inside the materials, which will diminish the mechanical resistance of the welding seams. So in the case of ultra short pulsed laser welding, we do not encounter such problems, and here I will overview some of the physical phenomena and processes that we are dealing with. So if we take, for example, a femtosecond pulse and we focus it inside a transparent material, the very small pulse duration will permit us to reach a very high intensity around the focus, where we can rely on nonlinear absorption regimes like the multiphoton and the tunnel ionization regimes. Just quickly, the multiphoton ionization regime, what it is, you can imagine here an electron in its well potential. So when we reach such intensities, the photon density will permit the electron to absorb almost at the same time several photons in order for it to gain sufficient energy to be released from the band gap potential. In the case of tunnel ionization, the strong field will distort the potential well, and the electron may tunnel through the potential well. But for my experiment, we are using more the intensity in the intermediate regime, where the electron will absorb a couple of photons and may tunnel through the potential band gap barrier. Other physical phenomena are related to the pulse's peak power, which will eventually lead to self-focusing if the pulse peak power is higher than what we call the critical power for self-focusing. So what happens when we achieve this is that we are relying on the optical Kerr effect, which states that the formula for the refractive index of the material depends on the wavelength of the laser we're using and also on its intensity. Normally, the second factor here is very small, so we don't consider it. But when we are using very high intensity and power regimes, this term becomes very important, and the consequence on the pulse is that it will see the material as a converging or diverging lens. So the pulse will be self-focusing at a position before the geometrical focus of the lens. And this will create kind of a first point of collapse here, and which will generate a plasma. But this plasma will have an effect on another part of the pulse, which is arriving at a time slightly beside the formation of this point, and it will defocus this part of the pulse. But it will eventually refocus to a position slightly beside the first one, and so on. So we will see several, due to the self-focusing and defocusing effect, we will generate several hot spots like this where there is a plasma is formed, which will give rise to the perception of a filament. So like a line of plasma which can extend between 10 microns up to 1 millimeter in length. So inside our filament, as I was saying, we have a plasma in which we have generated a very high free electron concentration, and it is accompanied also with a very high temperature. And since we are using extremely short pulses, the pulse duration is much smaller than the time it takes for thermal diffusion to take place in the material. So after the plasma formation and relaxation, we see a very fast cooling of the material. And that is a very big advantage for us to have limited thermal effects during our processing. And finally, the consequences of all this laser exposure is that in So, in the filament that we had generated, we see a refractive index change due to structural modifications of the material. So in comparison with the other laser welding techniques that I showed you, is that by exploiting nonlinear absorption phenomena, we have the possibility to join two transparent materials at the wavelength of the laser without any absorbent media. And since we have very low thermal phenomena also, it is an interesting process to join dissimilar materials. So the pioneers of the research on femtosecond laser welding of materials are a group from Osaka University in Japan, which had published their first paper about 10 years ago. And they stated in their research that here are the two important conditions to master an work in order to reproduce such phenomena. So the first one is to have an optical contact, perfect optical contact between the surfaces that we must join. And they use this, to achieve this, they use a clamping device that is illustrated here, where they will apply pressure in the center of the glass plates with a plano-convex lens, which will create a very small zone where we have sufficient contact for welding. And afterwards, they will focus femtosecond laser pulses inside this zone and at the interface between the two materials, and move the sample using a raster scanning technique in order to create a welded region. So, during my master's degree, I reproduced this method. These are personal results where you see the little point of contact here and several interference fringes. They're due to the popular Newton, the popular Newton rings, and they're caused by unequal deformations of the surfaces around the contact point. So a close-up of this point is inside the square here. We have the laser welded region where we can see a refractive index change, and as I was saying, the several interference fringes around. And the second condition to achieve a laser welded region is also to master the laser exposure conditions. So this same group, they drew two maps of laser conditions that permit successful joint regions for fused silica and borosilicate. So, as I stated before, several advantages of their technique. I would like to emphasize maybe on the fourth one, which is most interesting in my case with the industrial collaboration with Doric lenses, is that using this method, we may join transparent material without any adhesives. But there are always disadvantages to methods. And of course, we have to have a perfect contact state, which must be below lambda over 4, which lambda like the wavelength of the laser we're using, and at least one of the materials must be transparent. These two disadvantages we have to cope with. We cannot really eliminate them. But when I was talking to the engineers at Doric Lenses, they were telling me that a very big disadvantage is that we can only have very small joined regions, so only very small welded regions and small mechanical resistance. And again, if we want to join transparent media, it will be interesting to use their optical transmission properties. But the process as it is presented here, it affects the optical transmission properties, with the refractive index change due to the laser and to the surface deformations induced by the clamping device. So with these defects in mind, this is how I developed the objective of my PhD, is to develop a process for joining dielectric materials using femtosecond laser pulses, and we want the final assemblies to have the following properties. So Of course, we want it to be applicable to a wide variety of materials. We want it to have a strong resistance to thermal and mechanical loads, and we will want to achieve this by trying to have instead of having a very small contact point, trying to produce a bigger contacted region between the samples. And finally, we don't want the joined regions to affect the optical transmission properties of our assemblies. And of course, I'm doing a PhD, so it has to be some science in it. I cannot only do engineering. So at the same time, I will study laser matter interaction through filamentation and nonlinear absorption processes. This is the experimental setup that I'm using. It's a commercial reggae oscillator amplifier laser chain from Coherent. Just to go through the main parts of the laser system. Here is the pump laser. It's a continuous green laser which will pump both the oscillator and the amplifier here. We have a Titan sapphire gain media inside this, which will produce pulses at around 800 nanometers. So the seed pulses coming from the oscillator, I must mention, it's working on the chirp pulse amplification principle. So the seed pulses coming from the oscillator with very small energy, but very small duration, 20 femtoseconds, will be stretched here by a pair of gratings in order for them to go to the amplifier, to be amplified by a factor of 1,000. And then afterwards they are sent back to the grating pair to be recompressed into about 55 femtoseconds. So we use this method in order to avoid damaging the optics inside the laser. Another important characteristic of this system is that we can change the repetition rate between 10 kilohertz and 300 kilohertz. So that's, again, very interesting for processing of materials. On the other side of the table, here you have a drawing of the setup that I'm using. So the laser is coming this way. We have a pair of wave plates for control of polarization and power that will continue on to the remainder of the setup. And it will be focused by a lens here. We typically use microscope objectives. And our samples, we put them in the mount here, which is on 3D translation stages, and we have goniometers also for alignment. Now, to continue on to what I'm doing for my research project. In order to achieve a bigger contact zone between our two samples, engineers at Doric Lenses, they proposed to me to use direct bonding. And what it is we exploit van der Waals interactions between optical surfaces in order to bond them before going to laser processing. So here you have an example of, I don't know if you see the fringes very well, but you have an optically contacted zone here, and all the fringes that we see around is due to the sort of deformation or an air gap between the surfaces. After we have applied the direct bonding method, we've eliminated all the interference fringes. So it's very interesting technique for processing, because now we can weld this whole zone without generating ablation on the surfaces. But of course, there are some very specific requirements to achieve this process. We have to have polished and very flat surfaces, so we must adopt the proper polishing strategy. And the surfaces, before they're bonded, they must be very clean. Even a dust particle will not permit successful bonding. And finally, experience. It takes a lot of practice in manipulating the samples to be able to bond them this way. So when we bond our samples this way, they are quite mechanically strong, but they are particularly sensitive to thermal loads and the conditions that will deform the surfaces. I have a sample here that I will pass around. It's an example of two fused silica plates, like these ones that were direct bonded together. So as I was saying, it's particularly sensitive to thermal loads. So what we will do with the laser is that we will want to reinforce this direct bond by focusing laser pulses at the interface. So these are the conditions that I'm using. If we look like geometrically, how I'm positioning the focus is that, sorry for the figure in French, but we will place the geometrical focus of the lens slightly inside the second material, and relying on the filamentation effect and non-linear absorption, we will create kind of like this modified structural zone here on each side of the interface. Now, in the direction perpendicular to the laser's axis, we'll translate the sample in order to write several welding seams. Like, for example, we can use a rectangular welding pattern in order to seal the central region here. And if we want, we can also write another one to reinforce it much more, and several others also. So this way of doing is interesting because inside the central sealed region, we are not affecting the optical properties of the assembly. So as for results from this technique, samples like the ones that I've just shown you, it can support a thermal load between -20 to 500 degrees Celsius. And I did also a couple tests on the mechanical resistance in shear stress, and it could typically they can support 50 kilograms. But I had a special case where one of the samples supported 400 kilograms, but I didn't know what happened. Here in the image, it's microscope, SEM microscope images of the welding lines. So the pulses were incident from the top of the image, and the sample was translated like going outside of the screen. So each line that we see here is due to filamentation and structural modification. With the parameters that I'm using, I calculated that the pulse peak power is about 2.5 times larger than the critical power for self-focusing. So it is really due to, this effect is really due to filamentation and multi-photon and tunnel ionization. I've tried a couple of different materials combinations with using this process. Here are a few using like transparent and opaque material. The black lines you see here are due to the laser welding seams. I've tried also dissimilar glass. In this case, it was proposed by the company to try to seal like a thin film coating. And so we tried it, and it was successful both with between two fused silica plates and fused silica NDK7 plate. In this case, microscope images were quite interesting. The pulses were incident from the bottom of the image, so we still have a filamentation effect. But when the pulses reach the thin film coating, we have a linear absorption process, which damages much more the coating at this area. But again, we are using a sealing pattern. So in principle, the center here will not, its optical properties will not be affected. And we finally tried also on glass and metal configurations. as you can see here, fused silicon copper, pure silicon, and tungsten. I have other samples to pass around. You can take them in your hand, try to break them if you want. But what's interesting from all these materials that I've tried, if we look at the difference in their properties, I conclude that our process is applicable for a wide variety of materials. So, just reminding you again, the objective of my research project. I hope I've convinced you of how promising this method is. We think it is very promising, so we have applied for an international patent on this invention. Sorry. As I said before, I can't only do engineering during my PhD, I still have to do some science. So the next part of my talk, I will talk to you about the laser matter interaction experiments that I did. So the first one was a study of surface deformations in glass-based materials caused by femtosecond laser pulses. So using approximately these parameters, we would keep most of them fixed, and we would change only the pulse energy and the position of the focus inside the material. So as you can see here, we were creating damage tracks at different positions with respect to the back surface of the material. And what we noticed is that, let's say for a given position inside the material, we don't see any deformation. But when we move it further towards the surface, at a certain point, there will be the surface deformation that is generated. And we've measured all these deformations as a function of pulse energy and position in both BK7 glass and fused silica. So we conclude that the more pulse energy we put in and for a given position, the higher will be the deformation. Just to explain these graphs here, each line is for a different pulse energy. The horizontal axis is the position of the geometrical focus with respect to the back surface of our sample and the measured surface deformation. And during this study, we saw a lot of different interesting phenomena also. As you can see, like when we went for higher pulse energies of around 700 nanojoules, we saw melting and boiling phenomena on the surface. And we also noticed some nanostructurations inside these surface deformations. When we checked the literature on this nanostructuration effect, and we were able to produce it in conditions, experimental conditions, very different from all the articles and publications that we consulted. In these articles, they attribute the formation of these structures to microscopic breakage, matter, and a very big accumulation of constraints. The interest for us, from my experiments on weight welding, is that we have to avoid these phenomena because they will break the material. They will not give a big. They will diminish the mechanical resistance of our samples. So it is better to use moderate exposure, pulse exposure to our materials. Now, for future work. This is it will be a study of the damage track formation inside different glass-based materials. So I'm just starting this. These are very recent results, like 2 weeks ago, that I've taken these pictures. And what it is that the study of damage tracks induced by filamentation at different pulse energies. So as we would expect, the more pulse energy we put in, the longer will be the damage track because the filament that is generated will also be longer. So, and another interesting thing that we observed is that there's a cutoff right here between just smooth refractive index change, and optical damage, important optical damage that we can see in the other lines, and it is consistent with the literature on this subject. And in doing so, I compared it to compared my results to a simulation of the red dots are my results, and the blue line is a simulation of the length of the filament with respect to pulse peak power here. So you can see that it still follows a tendency, and I will try to reproduce these results, these damage tracks, inside different materials, going on with BK7, maybe move on to other more special glasses. And another part of my thesis will be to study and characterize nonlinear absorption, and again in different optical materials. I've already started to set up a pump probe transmission experiment, but as like an indirect measure of the nonlinear absorption inside materials when we focus femtosecond pulses inside. So these are preliminary results in the BK7 sample. Each line here is for a different pulse energy. In the horizontal axis, it is the position of the geometrical focus inside the sample and the measure of the normalized transmission. So it's interesting to see that no matter what the position inside the sample, the absorption stays almost constant. But near the front and back surfaces, we see these spikes here. And when we looked at the samples through a microscope, we saw very interesting phenomena like again surface deformations, like I talked about before, but also bubble formation. So it might be interesting with this experiment and microscopy, to characterize further the formation of these structures. And finally, last part for the future work is to develop applications for our patent. We think it's very promising. Just to go around very quickly, we think it has applications in this photoemissive semiconductors, lasers, inside construction of high power lasers, and can be used as a protection for solar cells or other features like thin optical coatings that we would want to protect also. So to conclude, the process that I'm working on is based on the improvement of two already existing techniques where we want to combine the advantages of both techniques. For results, I hope I've convinced you of how promising our patent will be. And I think in the domain of the laser matter interaction, there are a lot of interesting discoveries to be made in the future using ultra-short pulses. So this is all the team that has worked with me on these results. Just to point out, Professor Réal Vallée is my advisor at the university, and Dr. Sead Dorik is the president of Dorik Lenses, and along with his engineering team. Fabrice Lacroix is a French researcher with whom we collaborated on the patent application, and again research professional students who have helped me with setting up different experiments. So thank you for your attention.
Okay, probably someone with questions? No? Okay. Then I will ask a question. Can you show probably fifth slide? 7th.
Before or after? What's your question on?
I would like to ask you a question about how do you like make the sample going in a direct perpendicular direction, like
Oh, okay, yeah, yeah. How I align my sample with respect to the beam?
yeah, because
Okay.
you have to like to change the place. Here.
Yeah. Okay, yeah, it's of course it's very critical for my work because you can imagine when I'm focusing pulses inside the glass, the filament length will be between 40 and 60 microns, but we have to translate our sample on several millimeters. So of course alignment is very important, and that's why I have goniometers, and it's a technique that I developed by myself to get correct alignment. It's sometimes it's not so fun because it can take me about an hour at the beginning of my experiment just to align my sample. But what I've noticed is that when we're using very low pulse energy, okay, when I approach the sample to the focus, the focus of the laser beam, which is in the air, it will generate a kind of a little plasma, okay, that we can see with the naked eye. And of course, if we move our sample and it does not align, this plasma will disappear. So it's using like an iterative method that I'm searching for the position to produce this plasma on the surface and changing the angle of the goniometers in doing so. So I have to do it in like the horizontal axis and also in the vertical axis. And afterwards, and again maybe like for positioning inside the sample, I again rely on this small plasma that is formed on the surface, and then I move the sample towards the lens by a certain amount which I can calculate using the refractive index of the material. Okay, thanks. For those of you who weren't there at my previous talk, I brought some pens that I have left if you're interested to take some.
And here's some
Okay, and flyers of our research center.
Easy.
Basically on computer program that's for the environment Linux.
Okay.
And so it simulates like computer simulation of different things. And one of them is that I calculate like different properties of elements, like Fermi surfaces, all that, and density of state. And one of them is actually right now what I'm working on is the part where working with like kind of optics and lasers again. I got a little bit interested in that, and so one of them is based on an experiment, I guess. I already know the result of this experiment because I checked out the website, this like project.
Okay, and you're going to compare your
Yeah, so I was
to that.
so just wondering if it's like, I don't know, if popular because it's not as developed here, you know, like the computer simulation, especially for Linux,
Okay.
like a program that's just for Linux, not for Windows, not for Linux, just for that. So I was just gonna ask you about it, or if it's developing in Quebec or.
Well, for my particular project, no, not really, but it could be interesting to have a collaboration, because I'm better off, much better in the lab than to be in front of my computer trying to simulate and calculate. So, and I've already thought about this, like part of
Simulating.
simulating, but it's very complicated. When you're dealing with, I could show you the formulas. We're using the nonlinear Schrodinger equation.
Yeah.
So you have an idea what it is. So you can imagine all the terms that you have to add on. It's something that probably would be like a master's project. That's how big it is.
For like a simulation,
Yeah,
like
yeah.
other particles.
Yeah, like to generate the computer code
Mhm.
for this.
Are
And
you-
that's it. That gives you an idea how big a task it is. But it's because we're dealing with all these nonlinear phenomena. So
So that's why it is. No, it's just that I was just wondering about it because that's what my bachelor's is based on. So that's what I was asking about.
okay,
And pretty much right now for like condensed matter physics, basically what I'm working on is silica, and I've calculated a bit of the properties. Let's say density of state, and that took my computer like about 40 hours to just generate like a
Okay.
result that I can like graph later on. And like the graph is a 3D model. And basically, I've read that the only way that you can check if it's the right result, if it looks kind of like a shape or something like that, if it's all like chaos and you can't tell apart, this is like if it's any type of shape, then it means it's totally wrong and all your calculations are wrong.
so it probably has to follow like a known shape in mathematics, like a Gaussian,
Yes,
or
yes, yes.
typically when we're working in AutoCAD, you left that like the typical
Yeah.
shape for everything. Or,
But most of it isn't as developed, and I haven't found any like exact results. Some of them are
Okay.
like from a German university, I guess, and some of the results are graphed pretty well in 3D and all that. So I had something to compare it to. But for silica, there are absolutely no way that I can compare it with anything. So that was kind of tough. And then afterwards, I used another kind of algorithm, and I tried to insert an atom of oxygen into the structure with the silica. So, and
kind of like as like an impurity.
yes, yes.
Okay.
And I don't know, the result wasn't as what was supposed to, I guess, because the shape that I got was kind of a bit chaotic. But afterwards, I checked it again. I put my computer to a little bit more of a workload, and I got a result that turned out to be kind of symmetrical shape. Like most of it, most of the results, if they're symmetrical or like a bit, if the symmetry can be seen, a bit of symmetry, then it means it's correct.
Okay.
So that's what I got in my like latest result, I guess. So that's what I don't know.
That's
Yeah, that's that.
interesting though.
Yeah, so that's what I was wondering about, and I've asked. So, yeah, and I did check out that professor that you told that you should check out the professor who's also interested
Yeah.
in the brochure.
Yeah.
So I don't know if
Who was it?
I don't remember the name. Honestly, I can show you, but
Probably in this particular field, in like solid state? physics?
yes, solid.
Okay, I think it would be Bernd Ritzel. Not sure, I would have to check.
Yeah, I'm not sure. I've checked him out. Basically, I've seen some of the papers that he published, I guess, and I
Okay.
try to check it out and see if it's anything close to like condensed matter physics. But so that's what it.
Because, well, I was thinking of him because he's the guy who gave us our course on solid state physics.
Oh yeah.
And I know he's doing experiments with the attosecond laser system.
Mhm.
On this subject. I don't know exactly what he's doing, but
Is
I know
that-
he has a much bigger laser than I'm using. So
Is that the 10? What's the? You said which? Yours is.
yeah, minus femtosecond, attosecond,
That's 10 minus
18.
18, not 7.
Yeah.
No,
18. But of course he's using, it's like below one femtosecond, so that's why you call it an attosecond. But it will be like I don't know, like 500 attoseconds, maybe more.